Hello everyone, welcome. Today I want to introduce to my seed planter robot. This robot will help farmers to plant their seed. This is how the robot will look like. Let's talk about the part connection and function. Body frame material crafted from high-grade aluminum for lightweight strength, structural integrity, reinforced design to withstand a variety of terrain and weather condition. Shift and beam. Stability, provide the framework for the robot, ensuring balance and upright orientation. Movement, facility smooth navigation across the field, supporting wheel and motor assembly. We have also GPS mounted on the top for clear signal reception. Ultrasonic sensors strategically placed around the robot for obstacle detection. CPU, central processing unit, the brain of the robot, integrating integrated sensor data from decision making. Battery, high capacity lithium ion battery. Functionality of element, GPS and sensor integration. Navigation, GPS provide real-time location data, guiding the robot across the field. Obstacle detection, ultrasonic sensor. We have the obstacle detection, ultrasonic sensor, detect obstacle, sending data to the CPU for path adjustment. Actual and seed dispensing mechanism controlled by servo motor for precise seed release. Movement control, electronic motor drive the wheel with speed and direction adjustment by CPU. Energy system efficiency. The robot can stay for long operation hour, capable of running up to 8 hours on a single charge. Energy management, smart power distribution to optimize the usage and extend battery life. Key feature and design change, precision, ensure accurate seed placement within 2 centimeters of target. Autonomy, capable of navigating and avoiding obstacles without a human intervention. Durability, designed to operate efficiently for years with a minimal maintenance. Let's talk about the circuit design. Sensor, Arduino microcontroller. The Arduino serves as a central control unit for the robot. It receives input from ultrasonic sensor. The ultrasonic sensor is connected to the digital pin on the Arduino. Trick pin send out signal, and the echo pin received signal after it reflected off an object. The time difference is used to calculate the distance to the object. Actuators, DC motor. The DC motor are connected to the motor driver L293D IC on the breadboard. The motor drive is interfaced with Arduino and receive command to control the speed and the direction of the motor. Motor driver. Input pin are connected to Arduino digital pin for directional control. Servo motor. The servo motor is connected to one of the digital PWM pin on the Arduino, pin 9. In this setup, it is used for precise control of an actuation angle, likely used here for steering or another specific range of motion. Power supply, the 9-volt battery is connected to provide more power to Arduino on the breadboard through the Arduino voltage regulator to the servo motor and ultrasonic sensor. Electronic part, Arduino Uno, the brain of the robot. Motor driver L293D interfaced with Arduino to drive the motor, allowing for control of the direction and speed of each motor. Function together. When the ultrasonic sensor detects an object within a certain distance, it sends information to the Arduino. The Arduino processes this information and sends command to the motor driver to adjust the robot movement. Stop, move forward, turn, left, right. The servo motor used for precise movement and seed planting. This is a flowchart slide. Start, setup, loop start, read, serial, handle command, check, react to obstacle, movement decision, control servo, send the stats, and end loop. Let's talk about it. The input to the robot from the central control of others. Command. The robot receives textual command via serial communication. These can include instruction like start or stop, which control over all operation of the robot. From environment via sensor, ultrasonic sensor data, the robot uses ultrasonic sensor to measure the distance to obstacle in its environment. This distance data is used to make decision about movement. Process output of the robot. Based on command from the hub, start, active the robot motor, and starts operational routine, including movement forward and checking for obstacle. Stop, deactivate the robot motor. Based on ultrasonic sensor data, obstacle within 50 centimeter. If the sensor detect an obstacle within 50 centimeter, the robot will stop. Alternate between turning right and left each time an obstacle is detected within this range. No obstacle detect or obstacle beyond 50 centimeter, the robot continue to move straight forward. Servo motor, regardless of ultrasonic sensor data, if the robot active, the servo motor will keep working from 0 to 180 degree to provide precise movement and seed plant. Information transmitted to other or central control hubs data on sensor data. The robot sent back the following information via serial communication. This distance to the nearest obstacle as measured by the ultrasonic sensor. Current status of the motor, whether they are running or stopped. Example, output distance 30 centimeter, motor running, debugging information. For the debugging information throughout the code, there are serial print statement that provide real-time feedback on the robot action and decision, such as when it is decide to stop, turn right or left, or move straight forward. This robotic system is designed to interact with actual control hub through serial communication, receive command, process environmental data from its ultrasonic sensor, and perform action based on this input. It communicates its status and sensor reading back to the hub, which can be useful on monitoring, controlling, or coordinating multiple robots in more complex systems. This is the code. This code will make the robot turn left, turn right, stop, go forward, go back. When it see obstacle, also it can make the robot detect obstacle. And calculative behavior slide. Here we can see start, intention, all robot power on, and initialize their sensor and communication model. Central hub initialize and start listening for the robot status update. We have robot main loop. Each robot enters its main loop, which involves sensor reading, decision making, and communication. Sensor data calculation. Robot calculate data from sensor. Local decision making. Based on a sensor data, each robot make a local decision for navigation. Avoid obstacle, follow a line. It is communication with central hub. Robot send their status and sensor reading to the central hub. The central hub process this data, make a decision, and send back coordinating instruction, inter-robot communication instruction. So, for the inter-robot communication, robots share their status and sensor reading with each other. If direct collaboration is needed, we have also calculative movement decision based on instruction from the central hub or share data. Robot make calculative decision on their next move. Action execution. Robot executed the movement command such as turning, going straight or stopping. Feedback loop. We have also the feedback loop. After executing action, robot update their status and inform the central hub or other robot, completing the feedback loop. End loop. We have also last but not least, end loop continue. The loop continues with the robot constantly adjust their behavior based on a new sensor data and instruction. Now, let's talk a little bit about the demonstration and see what the robot can do in Tinkercad. So we can see over here. Now, now we will go to demonstrate what the robot can do in Tinkercad. Let's go. So here the robot, I will start it. Now let's begin here. Okay, right now. So let's try to turn to this side. So now the robot should stop and turn to the side, then go back, then turn, then go forward. Unfortunately, we don't have tire, so we cannot see the movement, and I cannot see if he goes left or right. So right now, go backward, check sometimes, then it will go, he will take one of the sides, and he will go forward again, or left or right. But now he's going back because he saw some obstacle here. I put some. Now, as you can see, he went forward. Now let's change the side to this side. Now we should stop and also do the same thing, go back, took one of the side, left or right, then you're gonna cross it, go forward. Now, let's see, stop, same thing. This is the servo motor that we talked about before. And right now, should go forward. This is minus. As you can see. Now, go forward, which is good. Now, let's try to go to 50 centimeter. Let's go 50. This is 50 centimeter. The robot should stop. Then go turn back, choose which side you want to go, left or right. And firstly, I didn't put screen. And there is no tire, so I cannot see in which side the robot is going. Cost analysis of the product. To estimate cost of my product, first of all, we need to consider the components manufactured, labor, and other overhead. GBS. Commercially available high-quality GBS units suitable for robotic can range from 100 to 500. Ultrasonic sensor, these typically cost between 10 and 50 per unit. CPU, a robust CPU for robotic application might be priced between 200, 1000. Battery, a high capacity lithium, as we say before, battery could cost 100 to $500. Aluminum frame and structural material, high-grade aluminum and other material for a durable structure might range from 200 to 500. Seed dispensing mechanism and motor, customized seed dispensing mechanism and motor, customized component could range from 100 to 500. We have also labor and manufacture. This varies greatly, but can significantly increase the overall cost. R&D, marketing, and distribution, these are additional costs that can be sustainable, depend on the scale and strategy. Total estimated cost, adding these components, are rough estimated for market ready. A unit could range from approximately 1,000 to 3,500. Here, market analysis on competitors, existing product, and the agricultural robotic market. There are seeding robot, weeding robot, and harvesting robot from company like John Deere, AgroRobot, and Harvest Automation. Value proposition, and investment justification. Invention and customer need. My design add a value offering position in seeding placement, autonomy in operation, and long operation hour, addressing specific need in modern agriculture. Comparison and cost and feature. While potentially more expensive, my design might offer better precision, durability, and energy management, justify the higher cost. Brand and market positioning. If my product is associated with well-known brand or target a niche market, it could command a higher price. Long-term benefit, empathize the cost saving over time, efficiency, improvement, and potential increase in crop yield to justify the investment. Direct composition. John Deere product. John Deere has a range of automotive farm tractor. I'm sorry. Farm equipment, including tractor and harvestman. They acquire Beer Flag Robotic, a startup specialized in and autonomous tractor. And John Deere product. John Deere product. John Deere has a range of autonomous farm equipment, including tractor and harvester. They acquire Beer Flag Robotic, a startup specializing in tractor technology. Feature: these machines are equipped with advanced system and sensor for effective self-driving capability. They can also function as a mobile hotspot to calculate data from sensor in the field. Price: specific pricing details are not readily available as they can vary based on the model and configure. Also, I couldn't find the price in the website. We need to contact them to get the price. We have also AgroRobot, a product AgroRobot specialized in agriculture robot, particularly for strawberry harvesting. Their robot uses a flexible mobile platform with up to 24 robotic manipulators to pick strawberries. Feature: the robots are designed to harvest strawberry gently, selecting only these that meet the farmer quality standard. This aligns traditional farming culture with cutting-edge technology. Pricing information for a group's product is not publicly disclosed as said. We need to contact them. That's what the website said. For the harvesters automation, a product harvest automation product details specific to most seed dispensing or precision agriculture are not exactly mentioned in the available source. Feature and the price. Due to the lack of specific information, it's challenging to provide detailed feature and the pricing for harvest automation in the context of most seed dispensing and precision agriculture. Why invest in this design? Unique selling point: highlight the unique feature like advanced GPS navigation, robust obstacle detection, and efficiency energy management. Target market: my product seem ideal for technology advanced agriculture operation looking for high efficiency and precision. Long-term reliability and efficiency. Stress the durability and minimal maintenance requirement, which can be significant selling point for long-term operational saving. Summary: the introduction discussed the concept of calculative behavior in the robotic and project objection. The technological design showcased the flowchart for robot interaction and explained the MATLAB code driving collaboration. Market analysis explored market readiness, budgeting, competitor, and our design value proposition, reflecting shared lesson learned in engineering design, business, and team dynamic. This presentation provides a comprehensive overview of the project, blending technical detail with market analysis and team management insight, reflecting a journey of learning, adoption, and innovation. Lesson learned: engineering design, iterative design, emphasize the importance of iterative process engineering where each cycle refined and improve the design. Integration challenge: gain a practical experience in integrating diverse components like sensor, actors and control system into a unified system. Stimulation with real-world testing, learning that stimulation, while valuable, cannot fully replicate a real-world complexity, highlight the need for physical testing and adoption. Entrepreneurial mindset, market research understood the critical role of comprehensive market research and defining composition and market opportunity. Cost effectiveness, develop an understanding of balancing cost with functionality and invention critical in a product design. Lesson learned also we have here. Management teamwork, effective communication, recognize the importance of clear communication and align team member with the project objective. Project management skill, improve skill in managing time, resource, and deadline, which are virtual in any object environment. A future project consideration, user feedback, a plan to involve end user earlier in design process for relevant feedback and better market align. Risk management, intend to adopt structured approach to risk management and identify and address potential issue proactively. Diverse skill utilization, aim to leverage the varied expertise of team member more effectively, fostering invention and collaborative problem solving. This is the recommends. Thank you for watching.